So I'm going to talk about jets. It is ultimately driven by Beck's, but I'm going to give a somewhat more general talk, and you will see the connection by the time I finish. Okay, jets. We have been living with jets, as has been mentioned before, for more than 100 years. The optical jet in M87 was discovered 1917, I think. And the radio jet since late 40s, 1940s, that is. And we got these amazing pictures. Cygnus A was shown in one of the previous talks yesterday, M87, etc. Many of these we have seen quasi movies where we can see blobs moving superluminally. And for a nearby source, M87, we actually have, I think this is a real bona fide movie made by Craig Walker. I believe this is 43 gigahertz, multiple snapshots. And we can see clearly there is some energy flowing out of this central object, the black hole. And we want to understand how these things work and test our ideas. And our ideas are very strong. We have a great theoretical model of jets. This is the model developed by Blanford and Znayak in 1977, which postulates that you have a rotating black hole with magnetic fields threading the horizon, held in by an accretion disk, and the interaction of the spin and the magnetic field causes power to flow out. And they came up with a nice force-free model, can calculate things. And I think by now it's the only model really that many of us believe, even though Roger was very cagey when Alex asked him, which of your many models do you like? He didn't want to pick one, but he did say that he liked working with Nayak. So anyway, this is the one for today's talk. It's a kind of a Penrose process. Penrose process was proposed in 69 with particles. Blanford and Snack is the magnetic field version of that same physics, where you're removing energy from a black hole. You could call it a generalized Penrose process. And the question for all of us is this really how nature works? Are real jets produced by a process like Blanford's Snack? We have got one booming answer from numerical simulations. Answer is yes. This started with people who developed codes for doing GRMHD simulations, Charles Gammy, Jonathan McKinney, and they showed in one of their early papers that if you put a spinning black hole, you get something that looks like a jet, power flow coming out. This became all the more solid when Tchaikovsky in 2011 showed that if you consider a system that happens to be in the MAD state, magnetically arrested disk state, then you get a really powerful jet, and it can dominates the energetics of the system far more than anything else that we normally consider in accreting black holes. Simulations also show that this MAD state, or at least a state with magnetic fields with the right topology, is pretty easy to make. It's kind of seems to be almost automatic, at least in my experience. I can't stop it. It always seems to be there. So I'm going to show just, everybody has seen these simulations. This is a simulation where we start with gas actually very far from the black hole. The black hole is here at 0, 0. The pressure maximum of this huge torus is at around 500 Rg. And even the least dense gas is at 250 Rg. So there's a big hole here. This is threaded with magnetic fields, which will go MRI unstable, create accretion, etc. And you can watch what happens to the magnetic field lines when I run the movie. And the one on the bottom right is an equatorial slice, just to show what's happening in the two cross sections. Okay, so 3D simulations. And what you see is, all this kind of curving of the field lines. That's kind of the MRI getting going. But the field lines are also being dragged along. And, pretty soon you see really nicely organized magnetic field lines. The stuff down here is the jet. That's the one that's going to be relativistic. But as you can see, there are these magnetic field lines all over the disk, and they're all nicely organized in this case. And the bottom line is, if you can give the system some nice poloidal field, which seems natural in an AGN, when the gas is supplied from a large distance, then it's all going to pile up in the middle. The field lines become a barrier, trying to stop the gas from accreting, but the gas will make its way. In fact, you can see in the cross section, magnetic field is strong in all of these green areas. That's all of these field lines. But the gas kind of squeezes through in gaps. So these are the so-called flux eruptions, and these are the streams. It's all very, very, typical of a MAD configuration. And as I say, they're very, very common. You have to work hard to avoid a MAD situation. Okay, I'll show the same guy again. This is just the big scale, the same simulation. But now it's going up to 10 to the 4 Rg. You can't trust the torus out here. It's not had time to reach steady state. But you can believe, I think, what's happening out here. The dark blue is the jet. That's relativistic. The more cyan and these lines, I'll call that a wind or a cocoon, which is surrounding and perhaps collimating the jet. And here is a jet that happily goes out to 10 to the 4 Rg, huge. And we can't do this on the computer. It'll go to 10 to the 8 Rg, I think, and it does in nature. And this being so natural and so powerful, and almost you have to do no work. You just need to write the code to run it, and then it'll happen. You'll get a jet. Suggests that this must be what's going on in nature. I'm going to show one more movie, which I really like. This is Kaushik Chatterjee's movie from, again, his simulation. And he has nicely colored the torus is blue. The jet is kind of, I don't know what that is, salmon. And then some lighter pink for the kind of the backflow from the outer jet. And I look at this picture and I say, man, this is Cygnus A. It's exactly the same shape. Of course, his jet is thicker than Cygnus A, but that is to a large extent just the resolution limits of what we can do on computers. Okay. One thing we have learned from these simulations is not only do these jets form, they can be really powerful. And if you write the power in the jet as some efficiency factor eta times your accretion energy m dot c squared, this eta, this is a formula that basically comes from BZ 77. It depends finally on how quickly your black hole is spinning, that's the omega, and how much magnetic field you have. That's this phi. And this phi goes as the square. So if you can make omega large and phi large, you're going to get the largest eta you can imagine. And you look at this coefficient and say, look, 0.004, where is it going to go? That's not a lot of efficiency. But the point to keep in mind is this phi is typically 50 when you're in the MAD state. And by the time you square 50 and multiply by 0.004, you're at eta of several, okay? So if you take a really rapidly spinning black hole and put it in the MAD state, you're going to get very high efficiency of order unity. Far higher than you could get from a normal Novikov-Thorne thin disk, which can give about 10%. This is 100%. So this figure, I think, was shown earlier. So this actually was first created by Tchaikovsky. Shows this eta in the jet as a function of, how do I move this guy? Do you guys see this? Share and all that?
No, we don't see
We
it.
don't see the boxes.
You don't see it. Oh, fine. Okay, it's bothering me. Okay, so these are honest to God simulation data points, okay? Happily following the theoretical expectations, eta values up to 1.5, and probably will go up to 2.5. We could really push spin close to 1. And the dotted line shows the thin disk, which is, and mind you, these are the luminous quasars. Our systems being radiatively inefficient, their disk luminosity, radiative luminosity, is less than this dotted line. But the jet mechanical power can be order of magnitude or more larger. Great. So I think I have done something here. Good. Can we confirm all of these theoretical ideas? Theorists are completely convinced. I'm convinced that this is the way it works, but now we have to actually show that it resembles observations or interpret observations and show that they are confirming the model. And we have a lot of the pieces already here, but there is one piece we are missing. We have wonderful intuition from analytic models. We have wonderful simulation data from GRMHD simulations. We have all the software we need to do ray tracing, calculate images, SCDs, movies, whatever you want. What we don't have is a way of translating our simulations to radio observations, electromagnetic radiation. We know what the gas is doing, we know what the magnetic field is doing, we know what the metric is doing, the black hole is spinning, all that is fine. But we have to finally translate it to something that describes the electrons and how they produce radiation. That is missing. We need to know what is the energy distribution of electrons and how are they distributed spatially. These jets start from the black hole and go to 10 to the 8 RG, right? You need to have a picture of the whole story if you can. So this is what I'm going to describe. This came with a paper that we wrote earlier this year. The two heroes are Youth Neto and Dom Pesci, and then a whole lot of other characters who kind of basically encourage them on. And the idea was basically this. We wanted to have a model that will take simulations or a toy model analytic, convert it into a real image or a movie. So let's look at the challenges. We know for sure from decades of work that jets have non-thermal power law electron distributions of Lorentz factor. You cannot use your usual R high, R low story, which we use in the disk. That's just not going to cut it for a disk, for a jet. We need to put power law spectra, power law electrons, which will then produce power law spectra. Another thing we know, many, many years, electron heating is not happening just at the black hole and then you spit it out. It's happening throughout the jet. You need to have continuous acceleration of electrons and heating them up all the way up to the end. So you need to put that in your model. We know that synchrotron cooling is important. Just because you produce an EDF by heating, it doesn't remain in the same shape. The highest energy Lorentz factors will cool rapidly, and if you wait a little bit, they're gone. They've all become lower gamma. So you need to include the cooling in your model. So all this needs to go in, and then you can make images, and hopefully they will look like observations. Now, people have actually done these things in various contexts, but blazars and GRBs are the two fields where it's been done a lot. And so for our work, we just borrowed this nice afterglow model, Sari et al., adapted it to our purposes. So through that, we got electron heating, we got synchrotron cooling into it automatically. And that part of the story seemed all right. Then we have to decide where to put these electrons. How should they be distributed? Over the jet. And here there's a clear clue. As we all know, jets are limb brightened. So here is a lovely image, NGC 315. Images of M87, this is definitely limb brightened. This looks limb brightening. Even the movie shows limb brightening. The edges are brighter than the center, and I would say even the 8 gigahertz. These are, very long distances. There is evidence for limb brightening. And there are many other examples. I just pulled out a few here. So we want to do this. And you look at it and say, yeah, this should be easy. Why? Because our jets, models, and simulations and everybody says that in a jet, most of the power flows along the edge. So here is a cross section of a jet. This is the jet edge. So sort to say, red is where you have a lot of pointing flux, a lot of power flowing. And the bluer thing is not much power going. This is the same story, but a cross section of the jet. And this is from a Tchaikovsky paper. Basically, all the power is going along the edge. So it's obvious. You put your the electrons have to be heated by the pointing flux. That's the energy source. So you put them in the edge, and sure enough, we are going to get limb brightened images. And unfortunately, the answer is no. Very puzzling when we saw it. It took us a few weeks. When I say us, we were all very worried, and then Youth NATO solved the problem for us. So this was his first result, right? He took this edge heating model And we were all waiting for this nice limb brightened jet. And what we got was a limb darkened jet. Look at this image. This is an image from a GRMHD simulation. Brightest in the middle, darker in the edges. Even though the electrons are distributed like this in cross section or like this in the poloidal slice, the image you make looks like this. So what happened? Where did our intuition go wrong? Here is the explanation, which at least you gave me, and then it made sense. So, here is the cross section. So all of your electrons are stuck to this yellow band here, okay? And you would say, if I'm looking at this from the side, I get a big path length here. So more electrons are radiating here. I get a smaller path length here. These two together are less than that. So it should be less, and I expect an intensity profile to look like this. But you have to remember that synchrotron radiation is produced by electrons spiraling around the magnetic field, and they beam, and the acceleration, the way it works, and the orientation of the velocity and all that. If you take a pretty roundish distribution of electrons, they like to preferentially radiate perpendicular to the field. So you may start with an isotropic distribution, but the radiation will not be isotropic. More radiation will come out perpendicular to the field, less parallel to the field. So here I have a lot of path length, but these guys are mostly radiating to the side. So it actually looks dark to me. Here I have less electrons, but they're all radiating towards me. And so they compensate for the reduced path length. And this is the kind of intensity distribution you get. Okay, now that was a big downer. But fortunately, you came up with a nice, I would call it a brilliant idea, though it's obvious in retrospect. He said, why are we assuming an isotropic distribution? It's a collisionless plasma. It can be anything. I'm going to use my freedom as a theorist to just postulate that the electron distribution is anisotropic. Anisotropic in the right way, so that instead of the beaming being like this, the beaming will be more parallel to the magnetic field line. And you can arrange this, okay? So he arranged this, he put it in his simulations, and we put it in our models. And sure enough, we got nice edge brightened jets. And what you need is electrons not being isotropically distributed, but more velocities parallel to the field, less velocities perpendicular to the field. So even though an isotropic distribution wants to radiate perpendicular to the field, by biasing things, you can make the radiation parallel to the field. And then you get the kind of limb brightening we want. So he put it in, and I'm showing just one picture. I'll show more pictures in a bit. Here is what he got. Instead of nice, previously a limb darkened and center brightened jet, now it is limb brightened and center darkened jet, kind of very much like the 86 gigahertz image of M87. This is, I think, the raw, clean image. So this gave us limb brightening. So that was great. And then the bonus was, it turned out there are papers in the literature which have argued that this kind of anisotropy is actually expected. It's not unusual. So there is, I'll just show this. I'll just mention the paper. Comesso and Cironi, they did real particle in cell simulations. The key is they were looking at low beta systems, which means very magnetically dominated plasmas. So in those conditions, which is a good description of jets, you expect electrons to be accelerated in such a way that they'll be highly anisotropic, exactly in the way you wanted to make the limb brightened jet. But in fact, here physics is telling us, yeah, that's how it works. So that was great. Okay. Now this was GRMHD. I should tell you, of course, that GRMHD, you can't believe the jets much beyond 10 to the 3 Rg. So Dom Pesci developed a whole separate semi-analytic model with all of this heating and cooling physics. It's all there, but it's a semi-analytic, very fast. It allows us to go to any distance we want from the black hole. And using that and the GRMHD, this is what we get with our model. These are observations. at 4 frequencies, 86, 43, 15, 8 gigahertz, different linear scales. I mean, look at the angular scales here. This is what the model gives, and it's wonderful. And mind you, it's not individually tuned, okay? It's one model which puts everything everywhere in the jet, and then you just observe it at different wavelengths, and they're all nicely tying together, giving a nice agreement with observations. Wonderful. Because now we can go and do this for any object we want, right? So these are two that you gave me probably 10 months ago, 3C273, 3C279. I think I'm running out of time. I'll tell you the dream with which we started. And I think the dream is still alive. The dream is, let's say we have a black hole with a jet, and we want to model it, or at least we want to predict for parameters what it should look like in radio. And then you can compare it with observations. So you've got this object, and let's say you are given the mass, black hole, spin the black hole, m dot, viewing. These are all, each source has got its own parameters. Either you don't know them already or you just try trial values, okay? And then you say, I want to look at the 15 gigahertz image or the 345 gigahertz image, whatever wavelength. So my dream is you give this to the theoretical modeler, and out will come an image which will show the intensity, the polarization, and everything. And maybe sometimes even a movie. That's what one would like to see from the theory end. And then you can judge, is this what the observations are showing or not? And if it's not, can we tweak parameters, or is it really a whole new piece of physics which we don't yet understand? We have these two methods, semi-analytic model and GRMHD. The semi-analytic model you can apply to any distance you want. It's extremely fast. So I've got one movie that Dom made for me. I think this is M87, but it's scanning all frequencies from 1 gigahertz to 1 terahertz as a function of time. It's just going up and down, up and down. We are also changing the inclination angle, and he has changed also the angular scale because, the jet becomes much longer at 1 gigahertz, and at 1 terahertz, it's small. So he's put all of this, and I don't know, I didn't ask Dom, but my guess is it took him less than 5 minutes, probably 2 minutes to make the frames in this particular movie. Okay, so we can do this. And this will soon be public, and anybody can play with it and make pictures. So you can scan parameters, but you can only make a time averaged image. I mean, you can play fancy games afterwards by putting by hand some variability, but it won't be real physical variability. GRMHD, on the other hand, is limited to small radii, up to 1000 RG, which is good. I think for BECS, that's the region we are interested in. But this can reveal the time-dependent dynamics and therefore can be converted to movies. You can actually watch the plasma moving. You can watch it accelerating. You can watch its polarization the way Elliott described. There is a lot of dynamics actually in this range, which BECS and its cousins should be able to observe. And I also want to make a point. If you look at the velocities in these jets, they are very, very spin dependent. So the 0.3 spin jet out to 1000 RG, that's the velocity. Doesn't go beyond beta gamma of 1. It's almost subrelativistic. 0.9, bang, it's gone up to a gamma of 3. Okay, and the other guys are in between. Anything you can observe on the dynamics, reliably if you can observe it and model it, is going to tell you the spin just from velocity, quite apart from all the other signatures that you could look for. Okay, so these are all things for the future, but I want to just stop here. This is my last slide, Peter. I think I ate up all the time. I'm sorry.
You're good.
These are movies that you made for me. 86 gigahertz, M87, M84, NGC 4261. These are all, our favorite sources. This is what the model says they should look like. Now we should go and measure them. 86 gigahertz, it's going to need a lot of ground coverage. BECS will give you the sharp features, especially closer to the black hole. And there are other caveats that I will go into if people ask. But basically, this is what we are talking about. This should be doable if you have enough sensitivity. So I'll stop here. Sorry, Peter. I think I went over time.
No, you're great. So that was terrific. Thank you. We do have a few minutes for questions. So people have queries to Ramesh. Michael, and then Sasha.
Yeah, just real quick question. These simulations are so beautiful, and it's amazing to see things that are so faithful to the GRMHD and the observations. I was curious if you just naively make polarized images of these of this model, does it get the magnitude of the polarization in the jet similar to GRMHD and observations, or is it similar to the modeling, the semi-analytic models on the horizon where you have to rescale that kind of arbitrarily?
This is a test we have not done. So in fact, we have got a clear understanding with the Princeton group. We both worked on this paper. The Princeton group will look at polarization, and for at least the first year or so, we won't look at it. The ray tracing, of course, has the polarization information. So it's clearly very interesting to ask whether the GRMHD in particular gives the right amount of linear polarization. So there should be, it can't be 70%. We know from observation, 70% is not correct. But how much less than 70 is it? I'm yet very unclear what the observations are showing. So we can check. One of these days you will do it. But we have been sidetracked by another project, which you has almost finished, which is, these are all so-called fast light movies. And slow light is awfully important for jets because they're coming towards us. So he's got all the machinery set up for slow light. And once that is done, we will look at the polarization and actually answer your question, Michael. Now, for the semi-analytic model, I think it's going to give a lot of polarization. So that is going to be very interesting, whether we need turbulent breaking up of the polarization signal even at large distances from the black hole. So I don't know the answer, but it's a great question. I think it's worth exploring, and we'll do it soon.
Thanks.
Thank you. Sasha.
Yeah, hi Ramesh, thanks for the talk, and I also like the questions that you raised about electron spectrum and their kind of directional distribution. So I wonder what higher energy observations like optical jet emission that we can kind of resolve sometimes and are getting better at this. Can it also inform us about the same aspect, just at the scales longer than what you are talking about here?
This model just postulates that there is a power law distribution of electrons, which then evolve through cooling and all of that, okay? But the distribution is very extended. So even while it is making radio and submillimeter, it's also making infrared, optical, and even X-rays, okay? So there is a prediction from this model for all the bands you're talking about. If it is inverse Compton, that will require more calculations. But as far as I know, for instance, the M87 jet, what HST sees and what Chandra has seen, they are all still synchrotron. It's just the tail of the distribution. So in principle, this model should reproduce all that. We can't use the GRMHD because those are usually further out. And there we can only do a steady state model, whereas we know from HST and Chandra that there are blobs. So we have to somehow handle the blobs. I'm not sure how to do it. But at the level of, if you smooth out the blobs, our model ought to be somewhere in the ballpark of those observations. Something that should be tested. Yeah.
Yeah, cool. Thanks.
Thank you, Ramesh.
Yeah, so that's the
terrific.
dream, actually. The dream is that it should be the whole SED and the whole, range of the spectrum, except for other processes like IC, inverse Compton. Okay, Peter, I'll get out of the way.
Thank you. That was terrific, Ramesh. Thank you very much.